Section: Introduction. We're going to talk about a new approach to training models that can understand both images and text. This is a hot topic in the field of machine learning, as it has a wide range of applications, from image classification to answering questions about visual content. However, current methods have some limitations. They're great at understanding the big picture, but they struggle with the finer details. For example, they might be able to tell you that a picture contains a dog, but they can't count how many dogs there are or describe their spatial relationships. To address these issues, researchers have started to experiment with new techniques that focus on the relationship between small parts of an image and individual words in the associated text. This approach has shown promise, but it's not without its problems. It's computationally expensive, it can be unstable during training, and it often relies on pre-existing models to get started. That's where our work comes in. We're proposing a new method called Sparse Fine-Grained Contrastive Alignment, or SPARC for short. SPARC is designed to understand both the big picture and the finer details. It does this by grouping together parts of an image that correspond to individual words in the associated text. For example, if the text mentions a dog, SPARC will group together all the parts of the image that show the dog. It then compares these groups to the words in the text, focusing on the most relevant parts of the image for each word. SPARC has several advantages over existing methods. First, it's more efficient. Many current methods compare every part of the image to every word in the text, which is computationally expensive and doesn't scale well. SPARC, on the other hand, only compares the parts of the image that are relevant to each word, which is much more efficient. Second, SPARC avoids the pitfalls of the winner-takes-all approach used by many current methods. These methods tend to focus on the most prominent part of the image for each word, ignoring the rest. This can lead to problems, as it often doesn't reflect the reality of the image. For example, if the text mentions a dog, the model should consider all parts of the image that show the dog, not just the most prominent one. Finally, SPARC doesn't rely on pre-existing models to get started, unlike many current methods. This makes it easier to compare SPARC to other methods and assess its benefits. In summary, we're proposing a new method for training models to understand both images and text. Our method, SPARC, is efficient, flexible, and doesn't rely on pre-existing models. We've tested it extensively and found that it significantly improves performance on a range of tasks compared to existing methods. We believe this is a significant step forward in the field of multimodal learning. Section Summary. Contrastive pre-training using large-scale image-text datasets has become popular for learning general vision representations, but these models often struggle with fine-grained visual information and localization tasks. To address this, we propose SPARC, a novel objective that learns representations encoding both coarse-grained and fine-grained information by computing similarity between image patches and text tokens. SPARC outperforms existing methods, avoids computational and memory issues, and allows for flexible matching between tokens and image patches. Section: Sparse Fine-Grained Contrastive Alignment. Let's discuss a concept called sparse fine-grained contrastive alignment. Imagine we have a set of image-text pairs, where each pair consists of an image and its corresponding text. We use two encoders, one for images and one for text, and two linear adapters. For each image, we break it down into smaller parts, or patches. We then convert these patches into a form that our model can understand, which we call patch embeddings. We also calculate a global vision embedding, which is a summary of all the patch embeddings. This is done by averaging the patch embeddings and applying the image adapter. Similarly, for each text, we break it down into tokens, or individual words or phrases. We then convert these tokens into token embeddings. We also calculate a global text embedding, which is a summary of all the token embeddings. This is done by averaging the token embeddings and applying the text adapter. Now, let's talk about the sparsity threshold. We set this threshold to be equal to the reciprocal of the number of image patches. This is based on the idea that each text token should correspond to at least one image patch. This threshold allows for flexibility in how many patches correspond to a single token, which can vary greatly between different images and tokens. This is useful in situations where we have detailed captions or when a single word is represented by multiple tokens. There are other methods for improving the fine-grained capabilities of vision language models, such as using pre-trained modules, specialized networks, and human annotations. Some methods involve matching image regions to textual descriptions through contrastive losses, while others add a cross-modal encoder on top of the dual image text encoder and use various techniques such as captioning, masked language modeling, image text matching, and bounding box prediction. In our experiments, we aim to compare different fine-grained objectives in a fair and consistent manner. We do this by re-implementing all competing baselines and using the same pre-training datasets, architecture, and number of training steps. We evaluate the learned representations across a wide range of tasks and datasets, from coarse-grained tasks like classification and retrieval to fine-grained tasks like object detection and semantic segmentation. Our method, Spark, improves performance on both coarse and fine-grained tasks across a number of different benchmarks. Section Summary. In the Sparse Fine-Grained Contrastive Alignment (SFCA) approach, we use a sparsity threshold to ensure that each text token attends to at least one image patch. This allows for variations in the number of patches corresponding to each token, enabling effective representation of objects regardless of size, scale, and shape differences. Additionally, SFCA achieves fine-grained understanding without the need for pre-trained modules, specialized networks, or human annotations, unlike other approaches in the literature. To compare the effectiveness of SFCA with other fine-grained objectives, we re-implement competing baselines and evaluate the learned representations across various tasks and datasets. Unlike some methods that sacrifice coarse-grained task performance for fine-grained understanding, SFCA improves performance in both coarse and fine-grained tasks across multiple benchmarks. Section: Experimental Setup. In our experiments, we used vision transformers, VITs, to encode images and transformers to encode text, following the standard practice in the field. We tested different versions of VITs, including VIT B32, VIT B16, and VIT L14, and paired them with corresponding language models. For the pre-training phase, we resized images to a resolution of 224 by 224 pixels and tokenized the text using a 32K vocabulary sentence-piece tokenizer, limiting each caption to a maximum of 55 tokens. We trained all models using the ADAM-W optimizer, a cosine learning rate schedule with linear warm-up and weight decay regularization. We used a large batch size of 16,348 and pre-trained the VIT-B models for 200,000 steps, equivalent to about 3.2 billion data points, and the VIT-L models for 250,000 steps, equivalent to about 4.1 billion data points. We first evaluated our model, Spark, on the task of zero-shot image classification. We tested it on ImageNet and several other datasets designed to test specific capabilities like robustness to perturbations and various distribution shifts. These datasets included ImageNet V2, ImageNet R, ImageNet C, ImageNet A, and ImageNet Sketch. Our results showed that Spark either matched or outperformed competing methods in all settings and across different VIT architectures. Spark was particularly effective at encoding information from larger patches, as shown by the significant improvements over baselines for VIT B32, especially on ImageNet R, C, A, and Sketch. We also evaluated Spark on zero-shot cross-modal retrieval tasks, such as image-to-text and text-to-image retrieval, on Flickr 30K and MSCOCO. Spark outperformed all competing baselines across all metrics. Finally, we assessed the fine-grained performance of Spark through a measure called faithfulness, which evaluates how consistent the model's highest-scoring caption is with the ground truth captions. This is different from Top 1 retrieval, which measures exact match retrieval and does not evaluate the model's ability to accurately describe the elements in the image. We found that Spark reduced hallucinations of objects while also showing competitive performance to related methods when taking all tokens into account. Section summary. The experimental setup involved using vision transformers, VITs, as image encoders and transformers as text encoders, specifically VIT B32, VIT B16, and VIT L14 paired with corresponding language models. The models were pre-trained using resized images and tokenized text, and achieved superior performance in zero-shot image classification and image text retrieval tasks compared to competing methods. Additionally, Spark demonstrated reduced hallucinations of objects and competitive performance in faithfully describing image details. Section: Fine-grained localization. We've taken a closer look at Spark by testing it on tasks that require precise localization, such as open vocabulary object detection and zero-shot semantic segmentation. We used the VIT B16 architecture for these evaluations. In the case of semantic segmentation, we followed the approach of previous studies and performed zero-shot segmentation using a text label. This means we calculated the patch embeddings of a given image and then determined the cosine similarity of the patch embedding with the text embeddings of all the ground truth classes. We assigned a matching class for each patch based on the text that had the highest cosine similarity with that patch. After that, we upscaled the patches to match the resolution of the ground truth segmentation and calculated the intersection over union, IOU, between the predicted and ground truth segmentations for each class. We then reported the average of the IOU scores over the classes present in the ground truth image. Our results showed that Spark significantly outperformed other models, improving the next best model by 4.34 MIOU on the Pascal VOC dataset and by 1.2 MIOU on the Pascal context dataset. We also found that Spark was better at object localization and predicting their shapes more accurately compared to CLIP. We also explored the use of Spark backbones in vision language models. Vision backbones trained contrastively from image-text paired data are often used in foundational vision language models such as Flamingo. We wanted to see if the improvements we saw with Spark would translate to better captioning performance in these models. To do this, we compared using a CLIP backbone versus a Spark backbone in a Flamingo-style architecture. We paired these with a frozen 400M parameter language model and trained perceiver resampler cross-attention layers to produce free-form text as output. We evaluated the models on captioning tasks on MSCOCO and Flickr 30K datasets. To understand the benefits of the different components in Spark, we performed two ablations, removing the sparsity on the similarity matrix and using softmax instead to compute the weights for grouping the patch embeddings. We found that both components significantly impacted the model's performance, with using softmax resulting in the largest decrease in performance. Finally, we looked at the computational and memory efficiency of the different methods by calculating the flops and peak memory usage for one update step for different batch sizes. We found that Gloria was as memory-intensive at batch size 4096 as other methods at batch size 16384. We also found that for Philip, the TFLOPS used for one update step increased by more than 200% between batch sizes 8196 and 16384, compared to a 100% increase for CLIP, Spark, and MGCA. For batch size 16384, both Philip and PACL had twice the peak memory compared to CLIP, Spark, and MGCA. However, CLIP, Spark, and MGCA use the same order of magnitude of flops and memory. For batch size 16384, the relative increase in TFLOPS and peak memory for Spark was almost half that for MGCA. Section summary. The Spark model is evaluated on fine-grained tasks such as object detection and semantic segmentation, achieving significant improvements over other baselines in terms of accuracy and object localization. Additionally, experiments comparing Spark with CLIP as backbones in a vision language model show that Spark leads to better captioning performance. Ablation studies demonstrate the importance of sparsity and the use of ment weights in the Spark model. Furthermore, computational and memory efficiency analysis reveals that Spark performs comparably to other methods while using similar flops and memory. Section: Discussion. In our study, we introduced a new approach called Sparse Fine-Grained Contrastive Alignment, SPARC, for detailed vision language pre-training. SPARC is unique in that it learns information at various levels of detail by contrasting both image level and caption level embeddings, as well as token and patch embeddings. Essentially, SPARC learns to group patches based on their similarity to tokens and then contrasts these language-grounded patch embeddings with token embeddings. What sets our method apart from previous studies is that this comparison is done within individual image-text pairs, eliminating the need for the computationally and memory-intensive task of comparing all patches and tokens within the full batch. Our comprehensive experimental evaluation shows that SPARC enhances performance on both image-level tasks such as classification and retrieval, and more detailed tasks like object detection and segmentation that require localization. Furthermore, SPARC enhances model faithfulness. While the simple act of making the similarity matrix in SPARC sparser already improves performance, we believe that exploring different sparsification methods and learning patch groupings could lead to even more informative representations. Given that SPARC learns patch groupings based on the associated caption, it would be interesting to explore pre-training data with highly descriptive captions in future work. Additionally, using bounding boxes and segmentation masks, in addition to image text pairs, could make learning patch groupings easier and improve learning efficiency, as the similarity matrix could be pre-sparsified based on these signals. Another exciting area for future research is to further investigate how SPARC encoders perform as part of multimodal foundational models like Flamingo, Blip, and Poly.